People asked about how do we know if two functions are the same or not? Because sometimes they look the same even if they're not, and sometimes they look different and they're actually the same. So here are 3 examples, and I will tell you that 2 of these are actually the same, and 1 of them is not. So, well, I'm going to give it away, I guess, but so let's look at this first one. So is f of x equal to 25 minus x squared over 5 plus x, and g of x equal to 5 minus x, are those the same function? In my mind, this is actually the one that's easiest to see that they are not the same. And they're not the same because they have different domains. So for 2 functions to actually be the same, they have to have the same input and output values. So for anything you can input for x, you have to get the same value out for y. And we can see pretty much right away here that in this problem, or in this function, g of negative 5 is equal to 5 minus negative 5, which is 10. Here, f of negative 5 is undefined. That's an automatic disqualification, right? If 2 functions do different things at the same input, even if one of those different things is being undefined, that means they're not the same function. Another way of saying that is they don't have the same domains. Which means, according to what I've said, that everything else on this board is the same. So let's look over here. This one, which is f of x equal to x squared plus 5x, and g of u equal to u squared plus 5u. These are definitely the same function. This is just a change of names, right? We've just replaced the x's with u's and the f's with g's. But really, it's the same thing, because for every input you can think of, each of these gives you the same output. F of 1 and g of 1 are the same. F of 2 and g of 2 are the same. F of pi and g of pi is it, right? No matter what you put in for the input, you get the same corresponding output. And then this is just one I wanted to kind of throw at you guys. These functions are also the same. The square root of x squared and the absolute value of x. I don't remember if I talked about this last class or not, but these are definitely the same function. No matter what you put in for x, you're always going to get the same thing out, right? F of 7 is the square root of 7 squared, which is the square root of 49, which is 7. And g of 7 is the absolute value of 7, which is 7. It also works for negatives. I think I've got enough room. F of negative 8 is the square root of negative 8 squared, which is the square root of 64, which is positive 8. G of negative 8 is the absolute value of negative 8, which is positive 8. And now that this is every possible number you could plug in, but we can kind of see, oh yeah, no matter what we plug in, if x is positive or if x is negative, both f and g give you back the corresponding positive number. And so really this is illustrating that the square root of x squared and the absolute value of x are actually the same function. So if you see the square root of x squared, you should think, oh, I have the absolute value of x. No matter what I plug in, if it's positive, I just get back what I started with. If it's negative, I get back the corresponding positive number. So this is what it means for functions to be equal. Most of the time when people ask you about questions like this, they're really going to ask you something like this, where they're equal almost all the time, except for maybe 1 or 2 spots in the domain where one of them isn't defined and one of them is. So these functions are not equal because one of them is defined in negative 5 and one of them isn't. All right, so that's all I wanted to really say about function equality. The thing you should be looking for with function equality is if one of the functions is undefined somewhere. That's usually a good tip off that, oh, they might not be the same. Or at least if they are the same, I should check out where one of them is undefined. The other algebraic thing that someone asked me about was some inverse function stuff. And these ones were, so usually with inverse functions, the process is pretty straightforward. In fact, we can do one that's not too bad. Like I'm going to ask this question this way because it's kind of a good question. I want to find the range of the function f of x equal to 2x plus 1 over x minus 3. So it would be possible that we could graph this function to find the range, but we don't really maybe have all the tools to graph this as precisely as I would like to. So instead, another way to find the range is by finding the domain of the inverse function. So I will point out that this function has a domain of everything but 3. So negative infinity to 3, union 3 to infinity. I know that wasn't the question that was asked, but I did want to mention it because it's important. And so then let's talk about the process of finding the inverse function. So to find the inverse, there's a couple different ways to go about it. I usually like to first write down my function as y equals whatever, 2x plus 1 over x minus 3. Then we switch x and y. And although this isn't hard to do, right, it's literally just write x where you see y and y is where you see x's. I do want to point out that at this point, this is where things have really changed. Once you have done this, you have interchanged, well, you've interchanged x and y, but more specifically, you've interchanged the role of the domain and the range. So that I can see here that it's already pretty clear that y can't be 3. So this inverse function that I'm about to find, whatever it is, I already know that 3 isn't in the range of this inverse function, which makes sense because 3 wasn't in the domain of the original function. So what I'm really kind of circling around here is that the domain of f is the same as the range of f inverse and vice versa. So the domain of a function is equal to the range of the inverse function, provided they both exist. And the domain of the inverse function is equal to the range of the original function. Which makes a lot of sense if you think about what we're doing, right? The domain is all the x things. The range is all the y things. If you interchange x and y, you're interchanging the roles of the domain and the range. So let's go ahead and continue with this. I now want to find, so I'm working on finding the inverse, and then I'm going to find the domain of the inverse, which will be the same as the range of the original function. So let's see, I'm going to solve for x. This is actually, so solve for y. The solving for y is actually the hard part. So I'm going to, usually it's best to get rid of any denominators. So I'm going to have x times y minus 3 equal to 2y plus 1. I'm going to multiply it out, so I get xy minus 3x equals 2y plus 1. And I'm trying to solve for y. So anything that has a y in it, I want to bring to one side. Anything that doesn't, I want to bring to the other side. So I'm going to write this as xy minus 2y. And I'm going to add the 3x over here to get 3x plus 1. Then I'm going to factor out a y. So I'm going to have y times x minus 2 equal to 3x plus 1. And lastly, I'm going to get y equal to 3x plus 1 over x minus 2. So, and then you can do this last step where you actually write the inverse function. So our inverse function here is 3x plus 1 over x minus 2. Okay, so let me ask you guys, what value is not in the domain of this inverse function? Exactly. I see some people writing it in the chat, or at least one person. It's hard to see the chat because I have it all up on all the people. Let me do one thing here. Okay, let me move the chat up a little bit so I can see a little more chat. There. Okay, oh, there's just one person. Thank you, Angel. I appreciate it. Yes, exactly. X can't be 2. So 2 is not in the domain of this, which means 2 is not in the range of this. But anything else is fair game. So the range here, the range ends up being everything except for 2. And that makes sense if you think about it. If you tried setting this equal to 2 and solving it, you would get no solution. Because you can multiply both sides by the denominator, and then the 2 x's would cancel, and you get like 1 equals -6, which isn't true. So yeah. So the point there really was to find the inverse, but I thought it was nice to also talk about how that has to do with finding the range of the original function. Let's go ahead and look at the slightly more complicated example that someone asked me about. I'm gonna change it up just a little bit because it's always good to change problems a little bit. Not always, but a lot of the time. Because I look at these ones, I was like, oh, these ones look kind of hard. Although I will say it's pretty similar to what we just did. So I think the original question was e to the x plus 1 or e to the x minus 1. I'm going to find the inverse of e to the 3x plus 4 over e to the 3x minus 4. I'm going to call that f of x. The one thing I will note is if you, gosh, sorry, I'm trying to like, sometimes I get too close and like it changes the lighting. I'm trying not to make anyone dizzy here. Just, I feel like the lighting here is always kind of funky. One sec. Oh, that's not what I meant to do. Sorry. Nope. Okay, I'm good. All right. I was having my adjust for low lighting setting on, but then it made the board harder to see. So hopefully everyone can see the board. If you can't see the board, let me know. So I want to find the inverse of this. Same steps. Y equals e to the 3x plus 4 over e to the 3y, e to 3x minus 4. Change x and y. The first two steps are kind of like nothing steps. You're just setting up the work. So then x equals e to the 3y plus 4 over e to the 3y minus 4. Be careful. I kind of wrote this badly. Kind of wrote this badly too. The way I've written both of these kind of look like the 4 is in the exponent, which it's not. I should be more careful there. And then we're going to try and solve for y. And it's really actually going to be very similar to the problem we just did. We're almost always going to get rid of the denominator. That's like number one step 99% of the time in these sort of, if you have a denominator, to get rid of it. So I'm going to have x times e to the 3y minus 4 equal to e to the 3y plus 4. And then we're going to multiply out the x. It's almost always a good idea to do that. I want to do that. Yeah, that's good. Okay. So I've got x times e to the 3y minus 4 times x equal to e to the 3y plus 4. And then, just like before, we can group all the terms that have a y in it on one side. So I'm going to write this as x e to the 3y minus e to the 3y equal to, I'm going to add the 4x over here to get 4x plus 4. Then I can factor. So this wouldn't work if the e to the whatevers had different powers. But since they're both e to the 3y, I can factor out e to the 3y. So I've got e to the 3y times x minus 1 equal to 4x plus 4. Leave that in the way. So then we can divide by this, right? Because we're trying to isolate y. To get e to the 3y equal to 4x plus 4 over x minus 1. You could factor out a 4 from the top. It's not super necessary. It's not going to make it really any nicer. It would be 4 times x plus 1, which doesn't cancel anything. So I would leave it like this. Now, in the previous problem, we kind of got to stop here. At this point, we have to do 2 additional steps. If we're trying to solve for y, we have to take the natural log of both sides. So the natural log of e to the 3y. In fact, I'm just going to write it here. Sure. So the natural log of e to the 3y is the natural log of 4x plus 4 over x minus 1. And then that is 3y. And then we would divide both sides by 3, or multiply both sides by 1/3. So that y would equal 1/3 times the natural log of 4x plus 4 over x minus 1. Yeah. And no, I think we'll leave it there. So that would be the inverse function. You could find the domain of this and then find the range of this. It is a little bit more work though. All right. Time is fleeting, so we'll move along. What I will say is, I will mention, there was another question that went along with this one that was to find the inverse of something like f of x equal to the natural log of x over the natural log of x minus 5 or something like that. And what I'll say about this is the process for that is very much the same, right? You would switch them up, multiply by the denominator, bring the y's to one side, the not y's to the other side. And then once you isolated your natural log of y, then you would have to do e to the whatever on both sides to get that y was equal to e to the stuff. But same sort of process. All right. So many things to talk about. Also, I don't remember, but I think, I don't know. No, I don't remember. It was either this class or my other class where someone was from Arcata. So if it's you who's from Arcata, that's great. I'm from Arcata too, which I said on the thing. So you already knew that. Where am I at? Okay, let's talk about limits. There's kind of a lot to talk about when it comes to limits. And really what I want to focus on today is not getting all this pen all over my hand, is the kinds of limits that you're going to mostly have to evaluate, which I think of are the 0 over 0 algebraic types. There are others, and we will get to them eventually, but as far as doing the limit definition of the derivative and your secant lines and your tangent line slopes, this is probably the most important thing for that type of work. So that's what we're going to start with today. We can definitely talk about limits to infinity and limits that are infinity. Maybe today, probably another day, but here's where we're at now. So let's look at some examples. I want to find the limit as, got to make some stuff up. Let's do this, yeah. As x approaches 5 of, sure, x squared plus 4x minus, so I'm really just making stuff up? Yeah, sure, 25. So there's a limit. And what I really want to kind of make sure you guys have at least heard a couple of times when it comes to limits is a limit doesn't care what's happening at the place that x is approaching, right? Whatever is actually happening at 5 doesn't matter at all. Limit is only concerned with the behavior of this expression as x gets closer and closer and closer to the number 5, but not actually equal to 5. And so I'm going to say that again in a minute after we've done some algebra. So here's what we can say. We can manipulate this expression. This is the limit as x approaches 5. I'm assuming this top part factors because I set it up so it would. Actually, I should stop for a second and point out that if you were to plug in 5, you get 25 plus 20, which is 45, minus 45, which is 0. On the bottom, you get 25 minus 25, which is also 0. So this would be what I often call a 0 over 0 type, or a 0 over 0 indeterminate form, which means we have to do some work. If you get 0 over 0, it means there is work to be done. 0 over 0 can end up being any value, or it can end up being undefined. So we really have to kind of do more exploring here. And usually what that means is you're going to have to do some sort of algebra. Not always. There's other 0 over 0s where you don't do any algebra. But in this case, we're going to use algebra, which is going to be factoring. Sorry, one sec. Got to admit some people here. So the bottom clearly factors as x minus 5 times x plus 5. And I know that since I plugged in 5 and got 0 on top, that x minus 5 has to be a factor. That's like the fundamental theorem of algebra. If you plug in a number and you get 0, that means x minus that number was a factor. And then the other factor has got to be x plus 9, because 9 times negative 5 has to multiply to negative 45, or 9 plus negative 5 has to add up to 4. Right? Oh, it works, right? It's the way it factors. And then, and here's the thing I want to point out. In fact, I'm gonna go away from this for a second. This thing I'm about to say is actually kind of very much related to function equality. So this function, f of x equal to the thing we're just talking about on the other side, x squared minus 4x plus, sorry, minus, plus, minus, sorry, minus, oh, there we go. So this function and this function, g of x equal to x plus 9 over x plus 5, right? Just taking the way we factor this and actually canceling those. These functions are the same except at one place. So these functions, f of x is equal to g of x, except at x equal to positive 5, right? Because here when x is 5, you get 14 over 10, and here when x is 5, you get undefined. Okay, so this is why the way we talk about the limit is really important. The limit as x approaches 5 cares about this expression everywhere except for when x is equal to 5. So as far as the limit is concerned, this expression and this expression are exactly the same, because the limit says, I want to know what's happening around 5, but not at 5. 5 can do things. So what that means is it is perfectly okay to say, well, I don't care that this expression is undefined at 5, that it's indeterminate at 5. That doesn't matter as far as the limit's concerned. I can totally cancel those out, and the limit of this expression is still going to be equal to the limit as x approaches 5 of this remaining expression. The only difference here is that this function is actually defined at 5, and this function is not. But they're both defined very, very close to 5.
You have x minus 5 on that.
Thank you. Appreciate it. I will say generally, if you see me making mistakes, let me know right away. I really, really appreciate it. It's going to make everyone's life easier. I definitely make mistakes. So then we can just substitute in 5 and get 5 plus 9, which is 14, over 5 plus 5, which is 10, which you can either write as 7/5, or I guess as 1.4. I would write it as 7/5. And we take a look real quick here. One sec. Yeah. If we look at the graph of this, which is much nicer, so it's really kind of, I mean, there's a lot of things I don't love about the current situation that we are all in, taking classes and teaching classes from home. But I will say, I gotta love that Desmos is really easy to show you guys graphs on because it's just super useful. So, sorry, I had a different graph set up to go before I want to show you this one. So let me just type this in here very quickly. What I want to show you guys is that something I imagine you might be familiar with already is that if I share this with you, there we go. Okay, so if we look at this here, we can see that everywhere except for 5, which can we get in there? Right, so right there at 5, it's hard to see if I zoom in a little bit. Sometimes you can't see the things as well. But this function is undefined at 5. Sometimes you can click on the thing and it'll stay there. It doesn't want to seem to do that today. Anyway, you saw it, you believe me, there we go. So right, this function is undefined at 5, but we see that on either side of 5, the value is very, very close to 1.4. So we can see that as we approach 5 from the left, the y values are getting closer to 1.4. As we approach 5 from the right, the y values are getting closer to 1.4. So graphically, I think it's not unfair to say that, yeah, we can see that from either side, the function values are closer and closer to 1.4, even though the function is undefined at 5. And yeah, stop sharing. Okay. And so that's why we're allowed to do the algebraic manipulation with limits that we want, is because whenever we're canceling stuff out, it is the stuff that doesn't matter because they're the places where the function is where we're taking the limit to. And at that point, we don't care if things are undefined or not. So there's a whole list of things we can do. And kind of the first thing, the first algebraic thing we usually do is just factoring and canceling. You can factor and cancel stuff. That is a perfectly good thing. And then, so I should say, right, whenever we're evaluating a limit, we're typically, after we've done some sort of canceling of some sort, we're then kind of checking back in and saying, can I now plug in the value that x is approaching and see if I get a limit that actually exists, as opposed to some 0 over 0. There's 2 other really common algebraic methods. Let me grab this other one here. Sorry, there's stuff all over the place. Yeah. So let's look at this one. Let's look at the limit as x approaches, sorry, 3 of the square root of x squared plus 7 minus 4 over, no, let's not make it too terrible. Let's just do x minus 3. So here's another limit. It's another 0 over 0 type. If I plug in 3 for x, 9 plus 7 is 16, square root of 16 is 4, 4 minus 4 is 0, 3 minus 3 is 0. It is good to check. Sometimes people will throw something at you that just happens to be like 1 over 5 after you plug stuff in, and that would just be 1 over 5. So sometimes people try to be a little bit sneaky, and they're like, oh, this one, you could just plug it in, you don't have to do the algebra. But oftentimes, right, it's going to be a 0 over 0 type. We have to do some sort of algebraic manipulation. So in this case, we can't just factor, right? I can't factor out an x minus 3 from the top. I can definitely factor out, I mean, there is an x minus 3 on the bottom, but to be able to do that on the top, I first have to employ a trick. And that trick or method is to multiply by the conjugate of the square root thing. So I'm going to multiply the top and the bottom by the square root of x squared plus 7 plus 4. And then it's got to be the same thing in the denominator. So right, the fact that I've got a square root minus a thing and a square root plus a thing, that's what makes those conjugates. And the reason we multiply by the conjugate is because it simplifies very nicely. When you multiply a thing minus a thing times the same thing plus the thing, you get the middle terms canceling out, right? Just as a reminder, a minus b times a plus b, that's going to be a squared minus b squared. In the middle terms, ab and negative ab just kill each other. They annihilate each other. So when I multiply this out, I get the square root of x squared plus 7 times the square root of x squared plus 7, which is x squared plus 7. Oh, I made a small error. That's all right. I'll fix it in a minute. And then the middle terms cancel, right? This times this is 4 times the square root of x squared plus 7. This times this is negative 4 times the square root of x squared plus 7. Those cancel each other out. So I'm not even going to write them down. And then we get negative 4 times 4, which is minus 16. So notice, right, we get the first thing squared minus the second thing squared. And here's a good rule of thumb. When you multiply out things that are conjugates, you want to multiply them out. But the other part of the fraction where the things are not conjugates of each other, you do not want to multiply it out. You just want to leave it as this factor times this factor. And we know this is a good practice because we know deep down that we're trying to cancel out this x minus 3. So we want to leave it already factored out so it's going to be easy to cancel it out. So I have an x minus 3 times the square root of x squared plus 7 plus 4. And now I want to point out a mistake I've made. It's not a big one in that it's easy to fix, but it is a big one in that it's a big kind of conceptual mistake. So here's the thing I've done. I forgot to write the limit here. And although it doesn't seem like that big a deal, it's kind of a big deal because this expression, the limit as x approaches 3 of the square root of x squared plus 7 minus 4 over x minus 3, this expression is saying, I want to know what this function is getting close to as x is getting close to 3. This says I have a function. They're totally different in meaning. So the reason I emphasize that is because I know it's easy to forget to write the limit, and I know it kind of seems like it's not a big deal, but your teacher probably feels like it's a big deal if you forget the limit because it is such a different meaning. So I want to really, really, really encourage you to every step of the way until you actually find the number that the function is getting closer to, we really have to write the limit as x approaches whatever it's approaching. I'll also point out, not that I've seen anyone raise their hand, but I can only see like 6 of you, just so you know, because my screen is pinned. So raising your hand will probably not be effective to get my attention. So writing in the chat or saying words, always effective. But not that I saw someone doing that, I just wanted to mention you probably won't get my attention if you're trying to raise your hand because I can only see I see 6 people right now. I try to scroll through every once in a while so I can see fresh faces, but often I don't. Okay, x squared plus 7 minus 16 is x squared minus 9. And we definitely can see, x squared minus 9 is going to factor in a way that makes sense to us. It's going to factor as x minus 3 times x plus 3 over still the same denominator, x minus 3 times the square root of x squared plus 7 plus 4. And now, since the limit doesn't care what's happening at 3, we can cancel the x minus 3's, right? Both this expression and this expression still get close to the same number as x is closer and closer to 3. So the limit, some people like this to plug in right here. I like to write more stuff. So the limit as x approaches 3 of x plus 3 over the square root of x squared plus 7 plus 4. And now I can go ahead and substitute in x equal to 3. This is called the direct substitution property, where you evaluate a limit just by plugging in what x is getting close to. It's going to be 3 plus 3 over the square root of 3 squared plus 7 plus 4, which ends up being 6 over 4 plus 4, which is 8, which ends up being 3/5. So notice, right, once I actually plug in the value for x, I no longer write the limit because now I'm saying, this is the number that the function is getting closer to or I should say the y values are getting closer to, as x is getting closer and closer to 3. Right. So yeah, I'll erase this in a minute. Our second method, our second algebraic method of tackling a limit is usually to do what's called multiplying by the conjugate. And in fact, things take longer on Zoom. I kind of want to have you guys do one, but I kind of want to, no, there's a lot of stuff to talk about. Let's do more examples. Okay, so the third method, the third algebraic method is, well, let's see, let me grab this here. Sure, that one looks all right. Let's do the limit as x approaches -3 of, what have I got here? Sure. 6 over x plus 1 plus, that's, yeah, sure.
Sorry, on the last problem, yeah, that step where you factored out x squared plus 7x minus 16, is that really the factoring, the x plus 3x minus 3?
Yeah, because 7 minus 16 is just minus 9.
Oh, it's not 7x
right,
minus.
There's no x here.
Oh, okay.
Yeah, very fair question.
Yeah, no, I didn't see that. I think there's like a reflection.
And I was being a little bit lazy and not showing every step there, right? A lot of times we would have written the x squared minus 9 as the next step, but limited space. Okay. Very fair question. So let's take a look at this problem and make sure we have to do stuff before we get going here. I plug in -3. Let's see, -3 plus 1 is -2. 6 divided by -2 is -3. Plus 3 is 0, and the bottom is definitely 0. So yes, it is a 0 over 0 tape. I don't know if I love the 0 over 0 type I've just come up with, because it's, no, it's fine. All right. So how do you want to tackle this? There's a couple of different ways, actually. Well, they're really the same. They feel different. So we're going to use a common denominator. And you either have the option of getting a common denominator in the top. So we could write it as the limit as x approaches -3 of 6 over x plus 1 plus 3 over 1 times x plus 1 over x plus 1 all over x plus 3. The other option is to multiply the top and the bottom of the fraction by that common denominator. So I can write it as 6 over x plus 1 plus 3 over x plus 3 times x plus 1 over x plus 1. Both of these will work perfectly fine. In my opinion, the first way feels slightly more intuitive. They're like, oh yeah, we're trying to add these fractions. Of course, we want a common denominator on the top. The second way may be slightly less intuitive, but is a little bit less work. Let me just show you both real quick. They're pretty much the same. So here, I'm going to have the limit as x approaches -3. On top, I'm going to have 6 over x plus 1 plus, I'm going to multiply this out and get 3x plus 3 over x plus 1 all over x plus 3. So little room. And then I'm going to simplify with the limit as x goes to -3. On top, I'm going to have, let's see, so I got a common denominator so I can add those fractions together. So 6 plus 3x plus 3 is going to be 3x plus 9 over x plus 1 all over x plus 3. A lot of people don't like this, where you have like a fraction over a fraction or over a denominator. It's not terrible, but we have to be careful. So I want to rewrite this as the limit as x goes to -3. the top here, I'm going to factor out a 3. So write that as 3 times x plus 3 all over x plus 1. And then instead of saying divided by x plus 3, I'm going to multiply by the reciprocal, which is 1 over x plus 3. But I want to emphasize, right? This denominator here is x plus 3 over 1. So when I flip by the reciprocal, it really is multiplying by 1 over x plus 3. And I feel like oftentimes this accidentally ends up in the numerator instead of in the denominator still. So just be careful there. And then we can definitely cancel the x plus 3 here and the x plus 3 there to get the limit as x approaches negative 3 of 3 over x plus 1. And then we can substitute in negative 3 and get 3 over negative 3 plus 1 is negative 2. So negative 3/2. So it's this kind of step algebraically that I feel like sometimes is a little wonky for this kind of question. The other option, which is this, which I'm going to erase up here so I can kind of show it there, is that if we do that, let me just go this way actually. We can distribute the x plus 1 to each of these terms here. So we have the limit as x approaches negative 3. X plus 1 times 6 over x plus 1 is just 6. X plus 1 times 3 is 3 times x plus 1. And in the denominator, we have x plus 3 times x plus 1. And if I simplify the top, bottom's still the same. The top is 6 plus 3x plus 3, which is 3x plus 9. And look, this is exactly where I was down here. I've got 3 times x plus 3 on top. I've got x plus 3 times x plus 1 on the bottom. And you don't have to do this weird flipping and multiplying thing. So, I mean, not that it's weird, it's just cumbersome. So either way of approaching this is perfectly good. I would encourage you to do whatever feels comfortable. I would like you guys to try one of these because I think it's worthwhile. So,
I have a question.
yeah.
On the other side, yeah. Where did you get the 3 over 1 to multiply on the first way to do it in the numerator?
So I had 3 here, right?
I'm referring to the other
Yeah.
side.
So
Okay, yeah.
So I was trying to figure out where he's. So here's what I had to start off with. This was the limit I was starting with, right? It is. And so what I did was I said, well, I want to get the common denominator in the top. So I'm going to multiply this by x plus 1 over x plus 1. And then what I did was to remind myself how to multiply fractions, I wrote the 3 as 3 over 1, just to make sure that I wasn't going to confuse myself somehow. So right, any number can always be written as a fraction with that number over 1. And we're still good.
Okay, yeah. Thank you.
You're welcome. Sorry, I lost a thing. Or I just, yeah, okay, fine. Black dust everywhere. Let me see here. Okay, yeah. So here are our algebraic methods. We've got factoring. So again, if we have a 0 over 0 type of limit, we can factor and cancel. We can multiply by the conjugate. Again, that's for square roots. And we can use a common denominator when we have fractions. So these are kind of the most typical ways of dealing with a 0 over 0 type of limit. Yeah, let me see. Okay. So let me give you guys one to work on your own, just to give it a shot. So why don't you try this one? The limit as x approaches, let's go 6 of 2 over x. 3 over x. I'm tired of this. 3 over x minus. All over, x minus 6. So go ahead and try that one. I will give you back. So let's work this problem, and then we will do some other things. There's so many things. Calculus is a whole wide world of examples. So this one does have an interesting a tiny little flavor twist that we want to address. So just as a reminder, we're talking about limits, talking about 0 over 0 limits, which this definitely is. If you plug in 6 for x, you get 3/6, which is 1/2, minus 1/2, which is 0, over 6 minus 6, which is also 0. So it's definitely a 0 over 0 type. And we are going to use a common denominator to evaluate it. So let's go right up here. And so what I should mention is that the common denominator of these two fractions that are being subtracted or added together, subtracted in this case, the common denominator is 2x. So one option, which I'm not going to take, is to multiply this by 2 over 2 and this by x over x. That would work just fine, but it's going to be slightly easier just to multiply the whole thing by the common denominator over the common denominator. It's really the same work for the most part. This is just a little bit less work. And just like with the conjugate, just like with conjugates, you want to multiply the conjugates together and not multiply out the things that aren't conjugates. Here, you definitely want to multiply out the 2x times the thing it is the common denominators of, right? 2x is the common denominator of 3 over x minus 1/2. And although we're going to multiply these together, you don't actually want to distribute that out. You want to leave this x minus 6 as a factor so it can cancel. So if something looks like it's something you're supposed to cancel out, you kind of want to leave it so you can cancel it out easily. So write the limit. In the denominator, we're just going to have x minus 6 times 2x. In the numerator, 2x times 3 over x. The x's cancel, and we get 3 times 2, which is 6. And then minus 2x times 1/2. The 2's cancel, and you get minus 1 times x, which is a minus 6. So that's what we're looking at. And oftentimes at this point, people just want to cancel things, but they don't quite cancel. It's 6 minus x and x minus 6 aren't the same. They are, however, opposites of each other. So you could either factor out a -1 and say, okay, -1 times, I'm left with a -6 plus x, and that is the same as x minus 6. And you could totally cancel these out. Or you could just say, I know that when I subtract things in the opposite order, they divide out and leave behind a -1. I've definitely seen people do this. They say these cancel out and leave behind a -1. Either way, it's fine. The rationale I always use is, right, 6 minus 2 over 2 minus 6, right? 6 minus 2 is 4. And if you subtract in the other direction, that's -4. And that's going to give you -1. And for any number you pick other than 6, this would always happen. The top and the bottom would just be opposite sides of each other. And so when you divide them, you would get -1. So this ends up being the limit as x approaches 6 of -1 over 2x, which is going to be -1 over 2 times 6, which is -1/12. So that's what the limit of this expression would be. All right. Not that we've talked enough about limits, because you can really never talk enough about limits. But I want to say a couple things about the squeeze theorem, and then we'll try and talk about some tangent and secant lines. Let's do a couple squeeze theorem examples. One thing I'll say about the squeeze theorem, not that this is always true, but you mostly end up using the squeeze theorem when you're trying to evaluate a limit that has a sine or a cosine in it. It can come up in other places, but a lot of the time it's when the insides of the sine or the cosine kind of are doing something weird. Like this example. So the limit is x goes to 0 of x times cosine of, what have I got here? Sorry, one sec. Of 10 over x squared. And so here's the real problem. Cosine of 10 over x squared is doing something weird, right? As x goes to 0, 10 over x squared is getting very, very large. And cosine of a very large number is kind of, right? I mean, here's what the cosine function looks like. Right, so this is just y equals cosine of x. If the insides of the cosine or the argument of the cosine function is getting very, very large, the y value of the cosine function oscillates between 1 and -1. Right? There's nothing we can definitively say about what this function is, what this function is getting closer to. So what I really want to say, although we haven't talked about limits to infinity, I'm going to say it anyway, is that the limit as x goes to infinity of cosine of x does not exist. This thing just keeps doing this oscillating thing, and we never get close to one particular value. Whereas all the other examples we've talked about, when you took a limit as x got close to a number, y got close to a specific number. And the same thing is true no matter what the expression looks like. So it's also true that the limit as x goes to 0 of cosine of 10 over x squared does not exist. Because again, the argument of the cosine function is getting extremely large, which means that the value of the cosine function is doing this oscillating thing. And I think it's really kind of good to see a picture of this. So let me actually show you. Sure, let me turn you off for a second. Sorry, one sec. Sure, there we go. Wow, that looks nuts. You should graph this on your own sometime. It's kind of fun. Let me show you guys. So if you look at this graph here, here's the graph of y equal to cosine of 10 over x squared. As you can see, it's definitely bounded above and below by 1, but I mean, it is just a blur, right? It just keeps oscillating up and down. So as I should say, as the x values get closer and closer to 0, so right, as we move along the graph, right, this way, we get closer to 0, and we just keep going up and down, up and down, up and down, up and down, right? It just goes wacky, and it actually oscillates between -1 and 1 an infinite number of times as we get closer to 0. Which means the limit doesn't exist, because for a limit to exist, the y values have to be zeroing in or getting closer to one specific value. And that is definitely not the case here if the y values oscillate between -1 and 1 an infinite number of times. So that limit doesn't exist. However, let me stop sharing for a second.
Sorry, wait, does that have a name real quick? As it oscillates infinitely between 1 and -1?
Not really. I mean, I would just say it's a no. There's no real good name for that. It's just a function that oscillates an infinite number of times between the y values oscillate between -1 and 1 as the x values get closer and closer to 0. So yeah, one sec. Sorry. So come on, thing. Sorry, my things are not always working for me. Apologies. So what I want to do now is talk about how you would use the, sorry. So that limit does not exist, but this limit's slightly different, right? It's x times cosine of 10 over x squared. And although this doesn't exist, it's still bounded between 1 and -1. So if you're going to multiply it by something that's getting really, really small, it will also probably get very small. So here's the algebra, and then we'll look at the graphical interpretation. Even though this thing has a limit that doesn't exist as x goes to 0, it is certainly true that any cosine or sine function, doesn't matter what the argument is, cosine of put whatever you want to in there, it's always between 1 and -1. Doesn't matter what's in there, right? We just looked at the graph, right, of that terrible thing, and it was always between 1 and -1. And now here's how the squeeze theorem or sandwich theorem usually goes down. You have some cosine or sine thing and some expression with other pieces. You write this inequality where you've got your cosine or sine of whatever is between 1 and -1. And then you manipulate the whole compound inequality so that the middle part looks like the thing you're trying to take the limit of. In this case, that just means we're going to multiply everything by x. So multiply by x. So I get -x is less than or equal to x times cosine of 10 over x squared. And that's less than or equal to x. And then, once the middle part looks like the thing you're trying to take the limit of, take the limit of the outer parts. So the limit as x goes to 0 of -x is just 0. The limit as x goes to 0 of +x is also just 0. So since the limit of this is 0 and the limit of this is 0, the limit of this gets squeezed to 0. So we can say by the squeeze theorem or the sandwich theorem, I just like to write ST, can mean either. By the squeeze theorem, the limit as x goes to 0 of x times cosine of 10 over x squared has to equal 0. Here's what's happening graphically. So back to this for a second. I don't need you, go away. So I'm going to turn this one off. So there's y equals -x, and we see that as the x values go to 0, the y values go to 0. Here's y equals x, same deal. As the x values get closer to 0, the y values also get closer to 0. And now here is 10 over x times cosine of 10 over x squared. And we can see that we are really stuck between those two functions. And so that since the upper and the lower boundary are both getting closer and closer to 0, the y values of x times cosine of 10 over x squared are also getting squeezed to 0 as we move towards 0. So that's what's happening. That's the squeeze theorem, really. It's kind of neat. And it really works for kind of anything with a sine or a cosine. Let me show you another example. Let me stop sharing my screen so you can see what I'm drawing.
You don't have to add anything that's in the parentheses of the cosine.
So one more time, sorry.
You don't have to add anything that's in the parentheses of the cosine,
No.
like the 10 over x squared.
Oh, well, do you mean like in the
inequality with -1 and 1?
Well, no. So it's in there, right?
Mm-hmm.
So what I'm saying is, it doesn't matter what that is. Cosine of take your pick. This part here can be anything. Cosine of anything is always between 1 and -1.
Okay.
Right, because if you remember, right, how cosine is defined, right, cosine of an angle is the adjacent over the hypotenuse. Or if you want to use the unit circle, right, it's the x over the r. I know it's been a while. Right, cosine of theta is x over r. X is always between -1 and 1, and r is 1. So cosine of any angle, cosine of any argument, always between 1 and -1. So yeah, let's look at something even crazier. Let's look at something like, let me change this one up just a little bit. So let's say I have y equal to, not y equal to, I want to find, sorry, the limit as x approaches 0 of 2 plus 1/4 x squared times sine of 20 pi over x. And that definitely looks terrible. And again, really, the hallmark of knowing you're going to have to use the squeeze theorem is you've got a trig function. And more importantly, you've got a trig function where the insides are doing something bizarre, usually kind of going to an infinitely large number. 20 pi over x, if x is going to 0, 20 pi over x is getting infinitely large or negatively infinitely large. So here's where we're going to start. We're going to start with sine of whatever you want to go in there. In this case, it's got to be the 20 pi over x. Sine of 20 pi over x is definitely between 1 and -1. In fact, just so that you guys really believe me, let me show you one quick here. So just like the other time, here is the graph of sine of 20 pi over x. And you can see that sine of 20 pi over x is really, really stuck between -1 and 1, right? It can't go above 1. It can't go below -1. It is really just jammed in there. There is no other option. So that's what we're writing right there. That thing is always less than or equal to 1, always bigger than or equal to -1. And then we're going to manipulate it. I want to have this in the middle. So first I'm going to multiply everything by 1/4 x squared. So -1 times 1/4 x squared is -1/4 x squared. And then less than or equal to 1/4 x squared times sine of 20 pi over x. It's less than or equal to positive 1/4 x squared. Be careful, if you multiply by a negative, you have to change the order of the inequality. Not that we have that here, but just something to remember. If you multiply by a negative, you have to change the order of that the alligator eats the bigger number, right? And then we're going to add 2 to every side. So I'm going to do 2, so plus 2, and then still minus 1/4 x squared, less than or equal to plus 2 plus 1/4 x squared sine of 20 pi over x. Less than or equal to 2 plus 1/4 x squared. And then now that the middle part looks like the thing I'm trying to take the limit of, and that's always our job, to make the middle look like the thing we're trying to take the limit of, we're going to actually take the limits of the outer parts. And here's what has to happen for the squeeze theorem to work. The limit of this and the limit of this have to be the same. Exactly the same. They can't be different even by a little bit. So the limit as x goes to 0, right? We have to be approaching the same value of 2 minus 1/4 x squared. I'm just going to plug in the 0 and get 2 minus 0, which is 2. And here, the limit as x approaches 0 of 2 plus 1/4 x squared is also 0. Sorry, not also 0. That would be wrong. What is it actually? Oh, someone already wrote the answer. Same answer as before. It's 2. And so this limit and this limit are the same. And since the outer things that are bounding this have the same limit as x approaches 0, this will also have that same limit as x approaches 0. So we can say that this limit is equal to 2 by the squeeze theorem or the sandwich theorem, whatever you want to call it. And if you want, you kind of see the manipulation of our function here. So let me show you guys. So here's my sine of 20 pi over x again. And then I can, what did I do? I multiply by 1. I don't want to do it that way. I kind of do. I don't really though. I really just want to do this. So here's the upper bound. Oops, I have to click on it. I don't want this one anymore. Here's the lower bound. And so we can see, without even drawing the inner function, that if we're stuck between this red and this blue function, as we get close, as x is closer and closer to 0, the y values are going to get closer and closer to 2, right? There's nowhere else to go. We are squeezed in between them. And then finally, we can see that one. Oh yeah, right? We are totally stuck. Pretty neat. I mean, the graphing stuff is kind of cool, I'm not gonna lie. So yeah, right. We are very, very much stuck, and we can see some values here. I wonder why they're giving me values here and not the other ones. Anyway, right? But you just go back and forth, back and forth, back and forth, and we get closer and closer to 0. It would still be undefined at 0. So if you actually click on 0 here, it is undefined. I don't think my mouse hand is that fine. Anyway, it doesn't really matter. So squeeze theorem. You're stuck between two functions. The two functions you're stuck between have to have the same limit so that the middle thing also has that limit. Okay.
I have a question.
Go ahead.
So we can use the squeeze or like sandwich theorem even when the limit, like if it's like x approaching like 6 besides 0, or is it only when it's 0?
No, it definitely works for examples that are not 0. It's just that 0 is often the example that it works for.
Okay.
So,
and then we use it when we do like sine and cosine? Usually.
I mean, technically the squeeze theorem can be applied really in a lot of different situations. It's just that most of the time it comes up is when you have a sine or a cosine.
Okay, thank you.
But that is not the only time. There are definitely other possibilities. All right. So let's talk about some secant and tangent lines. So I feel like the phrasing on some of these homework questions have been a little bit strange for our secant and tangent lines. So let's look at an example. Sure. I want to find the slope of the line secant to f of x equal to negative 2 over x at the point 2 comma negative 1. And another point that is, so this is the part that I think, and I've been seeing various homework things, I think a lot of them are asking to find like secant lines at a point, but again, secant line is supposed to go through 2 points. So I think the other point is supposed to be like another point h away. That's kind of what I'm thinking, is we're going to find the secant line that passes through the point 2, negative 1, and the point 2 plus h, negative 1 over 2 plus h. Let's draw a picture.
Wait, I had a question. I was wondering if you could explain like the y coordinate of the another point of like why it's like, yeah.
So what I'm doing for the y coordinate is I'm just plugging in the x coordinate. So for this one, right, I plugged in 2 and I got -1 because -2 divided by 2 is -1. For this one, right, I wanted to make my x coordinate h to the right. So I did 2 and I added h. And then to find the y coordinate, I'm just plugging in this x coordinate into my function. So just like this point here is f of 2, this point here is f of 2 plus h. Unless I'm making a terrible mistake, which I totally am, because I forgot the 2 up here. Sorry about that. Does that make it a little more clear now?
Yeah, thank you.
Don't be afraid to call out my mistakes. I definitely will make them on occasion. They're unintentional. They're mostly unintentional. Occasionally I'll make a real obvious, like winking at you. So this looks right? And then I'll be like, no, it's not right. But usually the mistakes are unintentional. This graph looks like this. Try and draw it kind of nicely here. Oh, something got flipped over. Sorry. Looks like this. So I'm going to give myself a little bit more credit here. Sure. So here's my point, 2, -1. And here's my other point, 2 plus h, comma, -2 over 2 plus h. And so I'm trying to find the slope of that secant line that passes through those 2 points. And so here's how we find it. So in general, the slope of a line between 2 points, right, we're just going to do the difference in the y values divided by the difference in the x values. So that's going to be f of 2 plus h minus f of 2 all over 2 plus h minus 2. So f of 2 plus h is this expression here. It's -2 over 2 plus h. F of 2 is just -1. And then 2 plus h minus 2 is just h. Usually for these secant line slope problems, if it's between like a point and a point plus h, the denominator is always going to be just that h. And so really, you can see this here, right? There's your rise, which is f of 2 plus h minus f of 2. And here's your run, which is 2 plus h minus 2, which is just h. So now we're just looking to simplify that expression, which, yeah, not a ton of room. Let's go to the other side. Let me erase the other side before I go to the other side. Sorry. So that's what we're trying to simplify, right? This is our slope. I want to point out, because this is where we're eventually going to go, if I was to let h be 0 right now, this would be a 0 over 0 form, right? The top would be -2 over 2, which is -1, plus 1, which is 0, over 0. So there's a reason we're trying to simplify this. It's so that eventually we can let h go to 0 and find the slope of the tangent line. So this is going to equal -2 over 2 plus h plus 1 over h. And just like with the problems we were doing before with limits, I'm going to employ some of those same algebraic methods. I'm going to simplify this by multiplying by 2 plus h over 2 plus h. So I'm going to get -2 over 2 plus h times 2 plus h is just -2, plus 1 times 2 plus h is 2 plus h, all over h times 2 plus h. The -2 and the 2 cancel. I get h over h times 2 plus h. The h's cancel. And I'm left with 1 over 2 plus h. And that is the slope of my secant line. So now, if we were to be asked what's the slope of the tangent line at the point, the way we find that is by taking the limit of this as h goes to 0. So the slope of the tangent line is equal to the limit as h goes to 0 of the slope of the secant line. Because what you're doing, I'm going to go back to this side for just a second, I'll come back. If we're letting h go to 0, we're letting this point move closer and closer and closer. So that the secant lines, which I don't want to draw them here because it's going to look terrible, but the secant lines get closer and closer and closer, right? It's this line, and this line, and this line, and this line. They get closer and closer to eventually being, and I ruined my picture, looks awful now, but they get closer and closer to being the tangent line. So that's really the whole idea here, is that if you take this expression for the slope of the secant line, and you let the h values get very, very small, you're essentially letting your rise and your run get very, very small, but in a way so that the slope becomes what the slope of the tangent line is. So in this particular example, it would be the limit as h goes to 0 of 1 over 2 plus h. We would just let h go to 0. And we get 1/2. So I'm going to say it again. The way we find the slope of the tangent line is by taking the slope of the secant line and taking the limit of that expression as h goes to 0, which is why we did all the simplification in the first place, right? If we just tried to do this, we couldn't just plug in 0 for h. Let's look at another example. Let's see. Let me look at my examples here. Not you. Sure. So I want to find the slope of the line secant to f of x equal to the square root of 4x plus 1 passing through the point where x equals 6 and x equals 6 plus h. That's the first thing we will have to do for this problem. Okay, so we want to find the slope of the secant line. Again, here is an approximation of what my graph looks like. Sure. Some kind of square root thing, maybe it looks like this. I'm obviously not drawing it to scale. Let's say that 6 is here and 6 plus h is way over there, just to make it easier to draw the things. Sure, I meant right over there. I'm right over there. So here is my point 6 comma, I'm not sure what that other y value is. And here is 6 plus h comma, whatever. I can find the y values by plugging into the function, right? By plugging 6, f of 6 is going to be, let's see, 4 times 6 is 24 plus 1 is 25. Square root of 25 is 5. And here it's going to be a little bit less nice. If I plug in 6 plus h, I'm going to get the square root of 4 times 6 plus h, which is that plus 1. So what I think, and again, I've only seen some of the homeworks, I feel like some of them are different. When they're asking for the slope of a secant line and they're only giving you 1 point, I'm assuming you're supposed to make your other point that point plus h. Right? I think that's what they're asking you to do in your homework problems. So again, we're just using the slope equation. I'm going to do the difference in the y's. I can totally draw a picture here. Yeah. Come on, pens. Pens. Right. So we're just doing the difference in the y's over the difference in the x's. I might be able to draw a nicer picture in a second. All right, so what we're going to do is we're going to do, so the first secant line is different. And it doesn't really matter what order you subtract in. I usually try to think of subtracting the more complicated thing minus the less complicated thing just because it feels nice, but you can kind of go either way. So it's going to be the square root of 4 times 6 plus h plus 1 minus 5 over, the denominator should just end up being h, right? It's going to be 6 plus h minus 6. Okay, what are we going to do to try and tackle this simplification? What algebraic method do we need to deal with this thing that, although it isn't a 0 over 0 limit yet, it's going to be a 0 over 0 limit once we take the limit as h goes to 0. So what do we need to multiply by? Yes, exactly, the conjugate. So I'm going to multiply this by, I'm going to tighten my board a little bit here first, sorry. By the conjugate of this, so it's going to be the square root of, I'm going to simplify this just slightly, right? This is 24 plus 1 is 25, and then 4 times h is 4. So this is really 25 plus 4h. That looks kind of gross. Didn't erase every answer. So it's going to be, the conjugate's going to be the square root of 25 plus 4h plus 5. And the same thing on the bottom. I should say, when we are simplifying these limits that are 0 over 0 types with an h in the bottom, or these slopes of secant lines with an h in the bottom, our goal is always to cancel out that original h in the denominator. Sorry, so these 6's obviously cancel. And then we really want you to cancel. You are public enemy number 1. We want you to go away. So this is going to equal, so again, when we multiply conjugates, you get the first thing squared. That's 25 plus 4h. The middle terms cancel, and then minus the second thing squared, which is going to be 25, or 5 squared, over h times the square root of 25 plus 4h plus 5. These cancel. And then you can say that 4h divided by h, the h's cancel. So we're left with 4 over the square root of 25 plus 4h plus 5. And so that's the slope of the secant line. Or I should say, it's the simplified slope, right? Because this also technically is the slope. It just doesn't look very nice. Here is our simplified slope of the secant line. So now, for the slope of the tangent line, this is not my favorite pen. It's going to be the limit as h goes to 0 of the slope of the secant line. Which is going to be the limit as h goes to 0. Also, just terrible. Of 4 over the square root of 25 plus 4h plus 5. So this part is just going to end up being 0. And you're going to get 4 over the square root of 25 plus 5. So that's 4 over 10, which is 2/5. Or 0.4, whatever you like. And so, again, just to emphasize the meaning here, what's happening is that this length here, which is h, we are letting that get smaller and smaller. So right, as we move this point this way, you're going to have secant lines that are closer and closer to what the actual tangent line is. And so, again, the slope of the tangent line is the limit as h goes to 0 of the slope of the secant lines. And where we're kind of moving with this is towards a definition of a derivative. Because one way, well, the way we typically define the derivative, or one, I should say, interpretation of the derivative, is the slope of the tangent line of a function. It's not the only way to think about it. It's really a rate of change, but that is one very common graphical or geometric interpretation. Let's see. I think there was something else I wanted to say here. No. Sure. Oh, I know what I did. Let's see. I think I have. I was playing around with some stuff on Desmos to kind of. Let me see if I've got what I want or not. Let's see here. No, that's not exactly what I wanted. Well, kind of. Sure. So let me show you guys this one. So here, so there's a lot of stuff over here, but what I want you to see on this graph, I've got the graph y equals x squared in green, and I'm looking at what's going on at the point 1, 1. And so you can see, so this line in blue is a secant line that goes to the point a f of a, where a f of a can be kind of anything on the parabola. And so if we slide this thing a little bit to the left here, right, we can see that as you decrease the distance between the 2 points, the line gets closer and closer to actually being the tangent line. And then, since I didn't write things in the simplified way, right, when my h goes to 0, my slope became undefined because I was dividing 0 by 0. But if I'd done the algebra to make this look a little, right, so if you look here, right up here is how I'm calculating my slope, right? It's y1 minus 1 over x1 minus 1. So when I end up getting y and x both being 1, I'm getting 0 over 0, which is undefined. So that's why the line is disappearing when I get over here to x1 equal to 1. But the idea is still that all of these are secant lines, and as we let the distance between the points on the secant line get closer and closer to 0, the secant line becomes a better and better approximation of the tangent line. And I don't know why that other blue dot is there. I tried to get rid of it. It's driving me crazy. Anyway, I thought that might be semi-helpful just to kind of see an example of what I really mean, right? That we are literally letting the points get closer and closer to each other so that the secant line looks more and more and more like a tangent line. So here is where we are going. Going to have some, it's too hot for tea, but my voice is, Mondays and Wednesdays are going to be challenging because 3 hours in a row is a lot of talking. So here's where we're going. We're going to throw this pen away is where we're going. That pen was trash. I think this one's a little better. So often we define the derivative of a function f of x at the point a as the limit. There's actually a couple ways of defining it, but here is the way we usually prefer. Limit as h goes to 0 of f of a plus h minus f of a all over h. It's typically how we define the derivative. Yeah. And again, right, it's the same, I mean, I've drawn the picture a couple times, but it's the same sort of idea, right? Where we're taking some function f of x, and maybe here's the point a comma f of a, and we're saying, all right, here's some other point, a plus h, f of a plus h, and the slope of that secant line is just this fraction or quotient without the limit, right? It's f of a plus h minus f of a all over h. And then as we let h get smaller and smaller and smaller, right? As we move this point over this way, so that h is going to 0, this secant line becomes closer and closer to this tangent line. So I know I've said this idea like twice already, but that's, again, the idea. And repetition is good, right? It's good to repeat yourself, right? I feel like I'm saying it too many times. I'm probably not saying it enough.